All right, we discussed Newton's first law last time. Newton's first law tells us how things are going to move if the net force on it is zero, right? Then what is the connection between the force and the motion of this object when the net force is not zero, okay? So that's what Newton's second law tells us. So Newton discovered that the relation, relation between the force and the motion of this object is not the force is connected directly to the velocity, okay, as a lot of people would think, okay. It's actually connected to the acceleration directly. So it's not connected to the velocity directly, okay. It's connected to the acceleration directly. So he also discovered that the relation is actually very simple. It's a linear relation, okay? So the acceleration of anything, a moving object, is always going to be equal to the net force on it divided by the mass, okay? And remember, it's a net force. That means you're going to add all these forces together as vectors, right? Divided by the mass of this object. And then if you rearrange the equation, you will get the net force equals the mass times the acceleration of the object. As a lot of people say, F equals ma, right? That's like the most famous physics equation. I believe everyone knows that, okay? So then the unit for the force, the SI unit for the force, is going to be the product of these two units, which is going to be kilograms times meters per second squared. And we do have a name for it, right? We call it Newton in honor of Isaac Newton, right? So the SI unit for force is the Newton, okay? But when you use this equation, you should be careful. First of all, always use net force on this equation, okay? That's, again, a common mistake people make. If there's a force in the problem, they just use the force, plug it into this equation, and then, oh, I'm just going to find the acceleration. You need the net force. So you should draw a Freiberg diagram, draw all the forces on this object, and then find the net force of this object. Divide the mass, you can find the acceleration. Secondly, this is a vector equation. Whenever you see a vector equation, you should be very careful, right? When you see vectors, you always work with components, okay? So when you use this equation, actually you're going to use that in x and y and z directions separately, okay? So when you use that, you actually should do this. The net force in x direction equals mass times acceleration in x direction. And then the same thing in y direction. So they are totally independent. These three directions. Okay? So when you work in x direction, forget about what's happening in y direction. They're totally independent. Okay? You only consider the forces and acceleration in x direction. Okay? And then when you move on to y direction, forget about what's happening in x direction. You only work in y direction. Find all the things in y direction, put them in this equation, you can find things you need. In this class, we're not going to go to three directions, okay? But that's what you're going to do. If you want to go to three directions, you're going to do the same thing, z direction, okay? So does Newton's second law agree with our intuition, agree with our experience? Think about it, right? Take a look at these three different cases on slide 17. If you want to move something, you definitely need to apply a force if something is at rest, right? And then what you're doing is that you use the net force, and this force cannot be balanced exactly, like canceled out exactly by another force, right? You will have some unbalanced net force on this object so that you can change the velocity of this object from 0 to some value, right? You want it to move. So you need to apply an unbalanced net force on the object in order to change its velocity. So that's acceleration. And then if it's the same object, you double the force, say, obviously you're going to see this object is going to move faster than owning like one force on it, right? The original force on it. So that's why the acceleration is proportional to the force, right? The larger force you apply, so the faster this thing is going to move, right? So the acceleration is going to be larger, okay? Agrees with our experience. And say if you apply the same force on a heavier object, right? If you apply the force with an object that has twice the mass than the original object, of course you feel harder, right? You feel, you're gonna see the object is gonna move slower because it's inversely proportional to the mass, right? So if you don't keep the force constant, you increase the mass of this object, you apply the same force on an object which is heavier, so of course it's going to get slower, okay? It may still move, it's going to get slower because the acceleration is smaller, okay? So Newton's second law does agree with our experience, okay? But again, if you want to make numerical predictions in physics, right? You need numbers. I want you to give me numbers. You need to use a law. You can't just use your intuition to get the right answer, okay? All right? So now let's take a look at an example. Now we're going to use this law to practice. We're going to practice this law in a real problem with real numbers. So let's take a look at this question. In a hockey game, two players strike the hockey puck simultaneously with the forces shown below. Okay, so you see there are two forces on this puck at an instant. The mass of the puck is 0.3 kilograms. We want to find the puck's acceleration. Okay, if you want to find the puck's acceleration, we can use Newton's second law and do net force divided by mass, right? But acceleration is a vector. Force is also a vector, right? You deal with vectors. You always work with the components. Okay, so that's what we're gonna do. We're gonna do this, right? We're gonna find the net force in x direction and divide by mass, then we're gonna get the acceleration in x direction. We're gonna do the same thing in y direction. We're gonna find the net force in y direction divided by the mass of this object, and that's gonna give us the acceleration in y direction. Acceleration is a vector. If you have these two components, how do you find the acceleration, the vector, the net vector, the magnitude and direction? You're gonna draw them out, you're gonna do trig, right? That's what we did before. Okay, so this is new, okay? So this law is new, right? But the vector analysis is still the same. You still need to use trig to, you draw out this diagram, you draw all these components, and then use trig to find things you need. Okay, so let's do that. Now, okay, so that's what we're gonna do. So we're gonna break it into different parts. Let's take a look at the first part. We want to find the x component of the puck's acceleration. Okay, so that's what I'm gonna do. The mass is given, right? The mass is 0.3 kilograms. So I only need to find the net force in x direction. How do I find the net force in x direction? Well, in this case, how many forces on it? These two forces on this horizontal plane, right? That's the only two forces on this plane. But actually, it also has gravity and a normal force from the surface, right? But these two forces, we know that the gravity, this is like the top view, the bird view, okay? You're looking at the top of the puck from the top. So gravity is down, it's actually into the page. If you want to draw the gravity, it's in that direction, into the page. What is the direction of the normal force? It's actually coming out, right? So these two forces, they're going to cancel out exactly, okay? Intuitively, right? And also, if you use Newton's laws in this direction, if we call the z direction in this case, nothing's moving, right? This puck is not moving in that direction, no net force, no acceleration, right? So velocity is 0. So we don't need to worry about z direction. We don't need to worry about this gravity and normal force, because they're going to cancel out exactly. They have nothing to do with this xy plane we drew here. Okay, so we're just going to focus on these two forces, right? Even though there are another two forces on it in z direction, we don't need to worry about it. Okay, so let's see. So these two forces, I'm going to break each force, because this guy is just going to be F1x plus F2x and divided by mass, right? This guy is going to be F1y plus F2y divided by mass. Okay, I just need to find these four components. Okay, so all you need to do, break Fy into x and y components. break F2 into X, Y components. Then add the components, you get the net force in X direction and in Y direction. Go ahead and use Newton's second law. All right, how do we break them into X and Y direction? Draw a new diagram. That's what I would do. I'm not going to draw everything on the original diagram. So let's draw F1. This is F1, right? The problem tells us that F1 equals 5 newtons. And then there's an angle 20 degrees with the positive X axis. How do you find the components? Right, I can draw them out. Okay, I don't need to remember any shortcuts, any conclusions. This is how I'm going to draw the X component. Right, you project it onto the X axis, and then this is going to be the Y component. So this is going to be F1X. This is going to be F1Y. Okay, and you do the same thing for F2. Right, draw F2 out. If this is I'm going to use the same coordinate system. So F2 is in this direction, and F2, the magnitude is 8 newtons, okay? And then it has an angle 60 degrees with the horizontal, with the positive X direction. How do you draw these two components, right? Again, projected onto X axis. This is what I would call F2X, right? What is the projection onto Y axis? That's going to be F2Y, okay? So these are the 4 components. These are the 4 components. Then you're going to use sine and cosine to find these components, right? If you have this diagram, then you can go ahead and find them, right? You don't need to remember which one is always cosine, which one is sine, because the problem may give you different angles. In this case, F1X, which sine or cosine? Well, it's adjacent to this angle, 20 degrees the problem gives me, right? So I'm going to write down cosine 20, that's adjacent, right? And then take a look at the direction of this component to the right in the positive X direction. So I'm going to call this component positive. That's how I distinguish left and right, okay? Now FY. F1Y, it's going to be this side, which is also this side, right? And this side is opposite to this 20-degree angle. So it's going to be F1 sine 20 degrees. Okay, now take a look at the direction. It's down. Okay, how do I distinguish up and down? How do I tell the equations that I'm writing a Y component down? I'm going to put a negative sign so the equations know, okay, you're plugging a vector, a component, Y component down, okay, not a Y component up, okay? Now do the same thing for F2, right? So you're going to break them into X and Y components, okay? Like what we just did, use sine, cosine, and take a look at the direction of these two components, okay? And then you can find the two X and Y components for F2. Then you go ahead, add X components together, divided by mass, that's acceleration in X direction, right? So now you can pause the video and find these two components and then find all these the components of the acceleration, right? Okay, so this guy, F2X, is going to be F2 cosine, again cosine, because the problem gives me this angle, okay? 60 degrees. Positive or negative? Well, it's to the right, positive. F2Y, F2, it's opposite, this side opposite to 60 degrees, sine 60 degrees, right? Positive or negative? Well, it's up. If it's up, it's positive. I don't need that negative sign, right? Okay, so what are the values? The values I got for this guy, the X component, it's 4.70 newtons, right? The Y component is negative 1.71 newtons, okay? What about this guy? This guy got 4 newtons, right? This guy 6.93 newtons. Now we can go ahead and find the x and y components of this puck's acceleration. Go ahead and add these two x components. They're both positive, right? This one and this one. Okay, you add them together, divided by the mass, which is the problem gives out the mass 0.3 kilograms. Okay, so this number I got at 29.0 meters per second squared. So this is the answer for the first part, the x component of the puck's acceleration. Now the second part, y component of the puck's acceleration. Add these two y components. This number and this number. This number is negative. Negative it is. Don't make it positive. Okay? So if you add these two components together, divided by the mass, you get 17.4 meters per second squared. All right, so now I have these two components. Doesn't matter what it's called, right? There are x and y components of a vector. So if I draw them out, what do I get? I would get this, right? So now I'm going to draw them out. I have two components of a vector. This vector is called acceleration, but that doesn't matter. This is the ax, right? 29.0 in the x direction. Now I have a y component of this guy also positive, so this is how I would draw the y component. All right, so I have these two components. How would you draw the net vector? Okay, well, I would draw it this way. So this is going to be the vector, whatever you call it, right? Now you're calling the acceleration, fine, acceleration. How do you find the magnitude of this guy? Well, that's just going to be x squared plus y squared square root, right? Pythagorean theorem. And then what is the direction? Well, okay, so that's the third part. How do I find the direction? In this case, I would just say it has an angle, theta, whatever this angle is, with this positive x direction, right? Okay, so that's how I would specify the, and then in this case, it's just going to be y over x, because it's going to be this side, y component over that side. Okay, now what is the magnitude and direction you got? The number I got is 33.8 meters per second squared. Okay, so that's the magnitude. What is the direction? You plug all these two components in, you get 31 degrees. So the acceleration has a positive, has a 31 degrees with the positive x-axis in this problem. So now I have the magnitude and direction of this acceleration. I know everything about this acceleration. Okay, so that's how we find the vector. So the only new thing is this, right? The Newton's second law. Okay, it helps us find the acceleration using the net force, but everything else it's vector analysis. We're going to be dealing with vectors a lot in this class. You definitely need to be very good at vectors. Okay. Okay, so we have finished this. Now let's take a look at the gravity. Okay, so we know that everything in free fall, okay, it's going to have the same acceleration, 9.8, down due to gravity. Okay, that's what we discovered in nature. That's what we have discovered in all these experiments we did. Okay, what is the reason for that? We're not sure. Okay. Why is everything in free fall has the same acceleration? Why can't they have the same velocity? Maybe in a different universe, okay? Not this universe, like things are different. The laws and theories are different. In that universe, when things are in free fall, they may have the same velocity. Or they may have an acceleration, but the acceleration is different, okay? Etc., okay? So in this universe, okay, especially on the Earth, okay, we have done so many experiments, we have confirmed that everything in free fall it's going to have the same acceleration, 9.8, and we call that number the constant little g, right? Free fall acceleration. So if I apply Newton's second law in anything in free fall, what do I get? I would get this. So let's draw the free body diagram of anything in free fall. So I would get, and then, oh, that's the only force on it. Let's call it gravity, right? So this gravity is the only force on it, and the acceleration is only in y direction, is also in this direction, right? So if I call this positive y direction, now I don't use up as positive, it's okay to pick down as a positive. Yeah? There's nothing wrong to pick down as positive or left as positive, okay? So in this case, if I use Newton's second law in y direction, what do I get? That's what I get, right? Okay, put all the forces on the left hand side in y direction. That's going to be only gravity, okay? If something's falling, and I call this positive y direction. Now, what is acceleration in free fall? Okay, little g. But now you're calling y direction, the positive y direction, down as the positive y. So I don't need to add a negative sign. Okay, I'm going to just put a positive number because I assume that down is positive. Okay, now you see that this is the equation you probably have learned to calculate the gravity of anything on the earth, like the force of gravity. You just multiply the mass by 9.8. This is actually a conclusion from Newton's second law, right? If Newton's second law is universal, it's also true in free fall. So the force on anything when they are in free fall must be equal to the mass times the acceleration, and if the acceleration is 9.8, that's how you would calculate this force, okay? And that's the most familiar fundamental force to everyone, force of gravity, okay? So that's the equation we use to calculate gravity of anything, okay? Now, once we have learned Newton's second law, we can even combine Newton's second law and the kinematic equations we learned before to make predictions. Okay, so let's take a look at an example on slide 23. So 0.6 kilogram model rocket, it was launched straight up. Okay, the small rocket motor burns for 5 seconds and has a steady thrust of 15 newtons. Find the maximum height the rocket reaches. Okay, so let's see. How do I find the maximum height, okay, of this rocket? So the rocket, when the rocket is launched, the motor has a force on it for 5 seconds, right? So I'm just going to, okay? It's just an object to me. It doesn't matter if it's a rocket, it's a ball, it's an airplane, a person, a car, right? It's an object. I'm just going to model it as an object. So it says that when it's launched, the motor provides a force, thrust, so which is going to be a force 15 newtons up, right? And then it has this gravity, right? But this force is greater than the gravity because you can calculate the gravity, okay? So gravity is still on it when it's launched. But this guy is going to wing, right? This guy is going to be greater than the gravity. So the what is the motion of the rocket? Well, it's going to be straight up with the acceleration up, right? And then, so it's going to move up and it's going to get faster and faster because there's an acceleration up. The net force is up, right, in y direction. So net force divided by mass is going to be acceleration. So in the first process, right, when it's launched, it's going to have an acceleration y up, okay, and then it's going to get faster and faster. But the problem says the motor is going to only burn 5 seconds. After 5 seconds, the motor is going to be off. So say this is after 5 seconds, okay. So after 5 seconds, the motor is off, so it's totally on its own gravity, right? So if only gravity on it, it's a free fall, right? So after that point, it's a free fall, but it already has some initial velocity at this point, right? Because it's been accelerating in the first process, okay? This is the first 5 seconds. It has an acceleration. So it's going to have some velocity here. So if you take a look at the motion after this point, this guy has some initial velocity straight up. It's like something is being thrown up at this point. So it's not going to stop here. It's not going to start to fall at this point, right? It's going to keep going up and then reach the top and turn around and then fall. So this portion, it's free fall, right? With an initial velocity up. So it's going to still keep moving up, slower, get slower, slower, reach the top, and then fall. Okay? So there are two different processes here. We're going to break it into two different processes. So we want to find the maximum height at this point. Okay? So that's what we want to do. So we're going to break it into two different processes because the acceleration is different. We can't combine them and use a theory for the whole trip, right? This is the first process, right? This is the second process. The first process is AY up with some value. We don't know, but we can find that. The second process is going to be free fall with some initial velocity. Okay. So let's do this. Again, let's break it into different parts. We're going to first find this height. Okay? The maximum height in the first part, and then we're going to move to the second part. Use this number to find the maximum height. So how do I find this height? If you want to find this height, and this is a constant acceleration motion, why? Because these two forces are constant on it. So the net force on it is constant. So the acceleration is a constant. If it's a constant force, constant acceleration motion, I can always use kinematic equations. Okay? So in the first process, I can use kinematic equations. So there are three equations, right? Which equation do I use? Okay, again, you can try it. So if I want to find this point, and I call this initial, this final, so obviously I'm trying to find YF in the first process. If I want to find YF, you can either use the second one or the third one, right? So let's try the second one. See if I can find that. If the second one doesn't work, I'm going to try the first one, right? Okay. So the first process, I'm going to try the second equation, which is YF equals YI plus VYI delta T plus 1/2 AY delta T squared. Okay, so that's the equation I'm going to use. Do I know YI? Okay, that starts from the ground. You can say ground is my origin. I'm going to assume this is Y equals 0. Okay, and that's the very common zero reference point people pick in the Y direction. What is the Y initial, the VYI initial? Okay, if it's launched, then the initial velocity is 0. It starts from rest. Okay. As soon as this motor is on, it's going to start to rise and then have some velocity. But the initial velocity at this point, 0. So 0 and 0, I have two zeros. Good, we like zeros. The only term I need to calculate, so it looks promising, okay? I only have to calculate one term. AY, the problem doesn't say. That's when you use this new law, this Newton's second law we just learned. I don't have the acceleration from the problem, but I can use Newton's second law to find acceleration if I know the net force in y direction divided by mass. Let's see if we have these numbers. The mass, okay, 0.6 kilograms, okay, good. I do have the mass of this object, 0.6 kilogram. What is the net force in y direction? You're going to take a look at the free body diagram. There are two forces on it, okay? One is up, 15 newtons. Don't forget gravity. Gravity is still on it, right? Gravity is on it. How do you find the net force? It's one is up, one is down. You subtract them. You don't add them because they are in opposite directions, right? So that's how you find the net force in y direction, right? You subtract them, you get the y direction net force, you find the AY. So you will have this number. What is the time? Do I have the time? Oh yeah, in the first process it says the rocket motor burns for 5 seconds. So that's the time for the first process. Okay, I do have all the numbers I need to find out the maximum height in the first process. Now you can pause the video, but finish the algebra and then find the maximum height in the first part. okay? All right, so what is the number you got? So AY, you're gonna first find AY, right? But remember the net force, Y direction is gonna be 15 newtons minus M divided by G, okay? Don't just use 15 newtons. A lot of people in this part, when we are starting a Newton cycle, they will make this mistake. Oh, there's a force one problem. I remember F equals ma. I'm just gonna plug the force in. You should be careful, right? People say F equals ma, but this F, it's always the net force. If there are like 100 forces on this object, you're gonna add all these forces together as vectors. Then you can divide the mass to get the acceleration. You cannot just pick one of them and plug it in and get the acceleration. That's wrong, right? That's not what Newton's second law tells us. All right, so in this case, and then AY is going to be this number divided by mass, right? Okay, so what is the acceleration you got in the first process? The acceleration I got in the first process is 15.2 meters per second squared. Okay, so that's the acceleration I'm going to plug in for the first process. It's positive because it's moving up, right? You see that the math, the answer is going to tell you everything you need, the magnitude and the direction. If I assumed y as positive when I do the algebra, the final answer is going to tell me if it's up or down. This is positive, so it's in the positive y direction. Plug it in, and then the time is 5 seconds. So this number I got is 190 meters. Okay, so that means this height is 190 meters, but this is not what I want to find, right? The problem says I want you to find the maximum height the rocket can go, because it's going to keep going after this point, right? It's going to get slower and slower because gravity is down, okay? But still going to go some distance in the y direction before it turns around. So that's what we want to do next. So the maximum height in the second part. The maximum height in the second part. So now I'm going to switch the I and the F, right? So now I'm not going to call this initial, this final. I'm going to call this guy initial, this point final, right? So all the values I found in this, at this point is going to become the initial values I use in the second part, okay? So I'm going to do it here. So now I'm focusing on the second part, the free fall, and I'm only interested in the rising part. So I'm only interested in this part, okay? So I call this point I, this point final, okay? So I still want to find YF, right? Remember, I still want to find this maximum height. So YF is what I'm trying to find, okay? Now, what is the YI in this process I'm interested in, which is this height? Well, this number is the number we just found, right? So the YI in the second process is the YF I found in the first process, which is going to be 190 meters. Okay, so I have YI, I'm looking for YF. Let's try this second kinematic equation again. Let's see if that's going to work. YF equals YI plus VYI delta t plus 1/2 AY delta t squared. So if I want to find this height at this point, the very top of this whole process, YI I know that, right? VYI I don't know, okay? I could find it, okay, but let's see if I have all the numbers I need, right? If this is too complicated, I'm just going to try the third equation. So I don't have this guy, let's put a question mark here, and I don't have the time, so I have two unknowns, okay? So it looks like it's going to be difficult, okay? Acceleration, okay, you don't need to find it, you don't need the problem to tell you, because it's a free fall, the second part. If it's free fall, you already know the acceleration, negative 9.8 meters per second squared, okay? Because I'm still calling up as opposed to y direction, so the acceleration plugging is going to be negative. Okay, there are two unknowns, I don't like that. One thing we can do is that try the third equation. The third equation also has YF in it, right? This is the third equation. So let's see if I have all the numbers ready for this equation. If I have all the numbers ready, I would pick this one instead of that one, right? If I don't have all the numbers I need, well, that means either one, I would have to find the numbers I need before I plug numbers into the final equation. VYF, that's the velocity in y direction at the top. Oh, that value I know, right? Because the top is a very special point if it's a free fall or projectile motion, because at the very top, the velocity in y direction is 0, right? In x direction, you're not sure, okay? Especially in the projectile motion, it may still have a velocity in x direction. But VYF, that's going to be 0, for sure. I know that. VYI, okay, I don't know. You see that? If I want to use the second or the third equation, VYI is something I can't avoid, okay? So, okay, there's no way around it, so VYI is something I need to find, either using this equation or that equation, okay? Now, let's see, 2AY, okay, AY, I already know that. That's going to be this number. YF, that's what I'm going to find, so I'm going to leave that there. YI is 190 meters. So the only thing I need is going to be YI. Okay, so first of all, my choice is going to be the third equation. It's going to have less steps. You can still find the YF using the first equation, but you just have two unknowns to find. You can still do that, right? You will be able to do that. The third one is better because I just need to find VYI. I don't need the time, okay? So I'm going to pick this one. Then, how do I find VYI? In order to find VYI, there's no way you can find it in the second process, right? Because if you want to use this, you have already used these two equations. They don't give you VYI. And then if you want to try the first equation, which is VYF equals VYI plus AY theta t, you could use this equation to find VYI, because you know VYF at the top, which is 0, the acceleration is negative 9.8, but you're missing time, okay? So if I want to find VYI, I'm going to need the time, but I don't have the time, okay? So looks like I cannot find VYI out of these three equations, okay? But don't forget the connection between these two processes, right? This initial point is the final point, right? So I'm going to go back to this. It's going to be the final point of the first process. So the VYI I need in this process, it's going to be the VYF in the first process. Can I find VYF in the first process based on all the numbers I have? Oh yes, because I already found the AY in the first process. So the easiest way to find VYF in the first process is going to be the first equation. Why? VYI, what is VYI in the first process? That's going to be 0. We already used that value in this equation. What is the time in the first process? That's 5 seconds. Okay? So I do have everything I need in this equation to find a VYF. So that's going to be my first step. Find a VYF in the first process, use that value as VYI in the second process, then solve this equation, find the maximum height, okay? So now you can pause the video and then find the, find the maximum height, all right? So let's see. The numbers I got, the first number I got for this guy, it's 76 meters per second, right? Because VY is 0, AY, we already calculated. Time, 5 seconds, put them in, you get the VYI. Now that's gonna be the VYI for the second process, right? 76 meters per second. Now you see, I have this number, 76, okay? So I have all the numbers in this equation except for YF, because the acceleration is negative 9.8 in free fall. I can rearrange this equation to get the YF. And then what is the YF you got? The YF I got is 485 meters. Okay? So this is this question. So what we learned in this question is that you can combine acceleration, you can combine Newton's second law with kinematic equations, right? Because Newton's second law can help you find the acceleration from the forces. And then once you have the acceleration, you can go ahead and use kinematic equations. Second thing we learned is that if there are different processes, you break them up, you split them up, the initial values of the second process, it's going to be the final values of the first process, right? If you need some initial values in the second process, you can try finding them in the first process, right? And then plug them into the second process as the initial values. Okay, so that's what we learned in this problem. So next time we're gonna discuss Newton's third law. So I'm gonna stop here for Newton's second law.